Three. Hi, Mark. Do you want to introduce yourself briefly?
Yeah, sure. My name is Mark Hamalainen. I'm the co-founder of the Longevity Biotech Fellowship. I've been working in the biotech industry for about 20 years, with the focus on developing the technology that would be required to indefinitely extend human lifespan.
Fantastic. So you're one of the few people that's actually working on a legitimate roadmap that's going to include all technologies needed for us to solve aging as a concept, as a problem, as a health barrier.
Yeah, I started off in academia and saw how slow the rate of progress was there, and also ran into the reproducibility crisis. I shifted gears and moved to California to do biotech startups in order to develop the tools and technology that would allow us to move faster. But after doing that for a number of years, including some projects that you might have heard of like Synthago, realized that the rate of progress was still too slow. This doing something about aging is just not a priority for our society right now, either from a funding perspective or a cultural perspective. And unless we scale up efforts dramatically by orders of magnitude, we're not going to solve this problem in the lifetime of anyone my age, potentially in the lifetime of anybody alive at all. So
Fantastic.
the roadmap is meant as a way to communicate to people what it would actually take if we want to achieve this goal, because there isn't, when you go to a longevity conference right now, you get to hear about a lot of specific research projects that people are working on, but there's no coherent overview presented of how we get from where we are today to a future where people don't have to age.
In your roadmap, you have a couple of categories, a couple of big basic categories that you think we need to focus a bit more on. One of them is AI, and a lot of people know about AI, but there's a lot more. And I'd love to learn a bit more about that from you.
Yeah, so if you look at the sort of biotech / pharmaceutical industry right now, it spends over $250 billion per year, mostly trying to develop drugs to treat the late stages of aging, the things like Alzheimer's and cancer and cardiovascular disease. We're focused on trying to take somebody who's already old and diseased and buy them a couple extra years or reduce their suffering during that time. And we spend huge amounts of money on this. The R&D is mostly focused on this. And then the healthcare system is also mostly focused on this. And for people that are young, they mostly just don't think about it. They don't really believe that it's going to happen to them until it does. And the research, funding for aging biology, for instance, is I think less than 0.5% of the NIH budget. The NIH is by far the largest grantor of academic research in this area. Other countries are sort of barely even measurable compared to it. So it's really not something that gets a lot of attention. And I think in the past, there was good reasons for that, because the complexity of aging is so great that you had to be either crazy or deluded to think that you could actually do something about it. But that's no longer the case. We understand aging well enough that we do have sensical ideas about how we could start intervening in it and preventing it and eventually obviating it altogether. But it takes a long time to change culture. It takes a long time to change institutions. And right now, we're not on track to implement these changes. And the changes mean a different way of thinking about interventions and therapies and healthcare. So the traditional pharmaceutical approach was designed to solve 20th century health problems, infections, things like that. We increased life expectancy a lot by treating infections and diseases that were preventable through pharmacological methods. But we've never actually increased lifespan. The maximum lifespan of a human hasn't been changed yet. We don't have a single therapy for aging. The longevity industry has grown a lot, and the anti-aging industry has grown a lot. This is mostly like Botox and exercise and diet trends that come and go. I wouldn't call, those don't actually affect lifespan either. The difference between exercising and not exercising is the difference between reaching your genetic potential for lifespan or committing slow suicide. People are trying to come up with exercise mimetics. People are trying to simulate having a good diet by coming up with mTOR inhibitors and fasting regimes and different things like that. But those don't actually affect, again, maximum human lifespan. And pharmacology, in principle, generally works by interfering with a protein or a metabolic pathway. The problem with that is it's not a good tool for tackling aging. Aging is thousands of your metabolic processes slowly, due to inefficiencies, because no chemical process is 100% efficient, accumulating damages and defects at the same time at about the same rate. And when your various metabolic processes start to drift outside of some range, some threshold level of damage, they just stop working properly. And then all of the other processes that depend on them also are hindered. And this is an exponential process. And so if you look at a mortality curve, it's exponential. It goes up exponentially. And that's because aging is an exponential process. And so the idea of trying to do something about that by just, taking a pill, doesn't really make sense. The main reason people think that way is because we have institutions and processes for making drugs. And so people just keep on, beating that dead horse, and it keeps costing more and more money to find fewer and fewer things. And that's just going to get worse. So you have to think of different approaches. And there's really only 3 ways that have been proposed that make sense. One of them is called replacement. We know how to make young human bodies. There's 8 billion people in the world. They're having children. When they have children, the children are not born old, they're born young. And so you can, in principle, just make young parts. Nature already knows how to do this, and we can just replicate what nature does. And 1 in 10,000 births, approximately, result in a person born without a functioning brain. These infants are not considered to be alive. They're euthanized. They don't have a mind, so there's nothing to kill. They're non-sentient, and there's no reason to keep them around. But you could imagine if you wanted a young body, why not just make a new one? So it's possible to take this natural example, learn about it, understand it, and then actually purposefully grow clones of your body that are young but don't have a functioning brain, so they're not sentient. And this is really no different than trying to grow a kidney for somebody who has kidney failure. It's just growing parts. It's not a person. It's just meat. And you could grow bodies and then transplant either your head or your brain onto the fresh young body. Having a young body is a really good way to for keeping an old brain alive. An old body is not very good at keeping a brain alive. A young body is very good at it. So you would get although you're not replacing the brain for obvious reasons, you do get a lot of benefits to the brain. The brain itself is also amenable to gradual replacement. So this has been demonstrated in animal models of stroke and other things, where you can replace parts of the brain that are damaged with fresh, young fetal tissue grafts that you grow in labs. So you can make graft tissue that is sort of similar to an early fetal stage of development, and you can implant that into the brain. And the brain is actually shrinking as you age. So if you just add material to complement that shrinking, you'll be gradually replacing the old parts of the brain with the young. You might ask, is this going to cause problems with memory or identity? Well, no. I mean, people have, we know that function migrates within the brain. People get benign tumors in their brain that can sometimes take up a pretty large volume of the brain. And sometimes this happens, for example, right in the language center of the brain. But these people never lose the ability to speak. The function just migrates. And so through the combination of the fact that the brain is shrinking, and also you could also purposely induce gradual silencing of parts of the brain at a rate at which the memories and the functions can migrate. And then you can add new tissue. And so this can just be done periodically. And it's like the ship of Theseus. You just basically are always replacing old parts with young. And so you stay alive. This, in principle, could work. And there's actually budgets with specific, there's a roadmap with specific budgets and time estimates. And it's not even very expensive. It's actually to actually test this in animal models and prove that it works. The amount of money required is actually a rounding error on the amount of money spent on pharmaceuticals that barely work, if at all. And so it doesn't really make sense that we're not pursuing this aggressively, because it has the potential to extend lifespan, alleviate suffering at a much greater, more potent level than the ways we are going about it today. So it needs a lot more attention. There's only a few people in the world working on this, a few companies, a few labs. Now there's another technology that doesn't get a lot of attention, which is reversible cryopreservation. For a lot of people today, they're already old enough that they're not going to benefit from seeing technologies like the one I just mentioned fully developed, because that takes time. We're looking at 20 years to get that technology to maturity, assuming that we fully funded it, which currently we're not doing. And so cryopreservation is another area that's cool, because you don't actually have to understand how aging works, the same as in replacement. You don't actually have to understand how aging works in order to replace parts. With cryotherapy, it's a physics problem. It's how do you freeze somebody without damaging their tissue so that they could be revived later when we do have the technology to make aging and diseases obsolete. This has been a sort of a backwater field with chronically low funding. There are many very good and very promising proposals for how to make this work. Some of them involve chemical cryoprotectants. There's also physics tricks in terms of how you actually do the cooling and warming rapidly, which is important to prevent ice crystal formation, which is what causes the damage that is associated with freezing somebody. There's also animals that can be frozen and thawed and are perfectly fine. The Arctic tree frog, I think it's called. It's part of its life cycle is being frozen for 200 days of the year, and it wakes up as perfectly fine. We could study how these animals do this, and we could use gene therapies or just understand the principle and develop chemicals or physics methods to replicate this in humans. And so this field gets almost no funding, but if it was funded, we could probably, it's reasonable to assume that we could actually fully develop this technology and have it working in the order of 10 years. So that would save a lot of people's lives. Even if you just get into, it doesn't even have to be for aging. It can just be for any disease that you get that there's no cure for. You could just be effectively put your life on pause until a cure is available. It may sound kind of weird, but again, like I said, other animals in nature do this. It's not unnatural. It's just that humans don't happen to have this capability. Another area that does get attention is more advanced bioengineering. So you could think of pharmacology as the most primitive form of bioengineering. You're trying to modify biology by just mixing in chemicals and interfering with the function of proteins. And sometimes that's great, because sometimes you can interfere with the production of cholesterol and reduce the amount of cholesterol in your bloodstream and lower the rate of cardiovascular disease. But most of aging is not. It's not like we have some latent ability to live forever that you can just activate with a drug. That's not the way natural selection works. Natural selection doesn't give you traits that wouldn't apply after your extrinsic causes of death are sort of giving you a sort of an upper time limit. The mathematics of how natural selection works to set the lifespan of any given organism is actually quite interesting and well understood and modelable computationally. We know this. There is no magic. There's no there's no aging gene that you can interfere with a drug and then all of a sudden we won't age anymore. That's just not, unfortunately, the way it works. It would be very convenient. And a lot of people pursue the strategy simply because it would be convenient if it was true and because it's grammatically correct to make a statement that I'm going to look for an aging drug. But just because it's grammatically correct doesn't mean that it's logically correct. So the advanced bioengineering approach would be to actually understand biology enough by collecting enough data, building comprehensive and accurate models of biology, and then that can predict, say, if you wanted to make genetic modifications to make us live longer, which modifications should you make? That doesn't break any law of physics. We already see in nature that there's an incredible diversity of lifespan. There's a lot of things that live longer than us, and different branches of the evolutionary tree have evolved ways of living a long time that are not the same. Evolution happens from random mutations, and so when you go down different branches, the mechanisms by which nature has achieved longevity are not all the same. Elephants, for example, have dozens of copies of tumor suppressor genes instead of just 2 like we do. And so you have to accumulate a lot more mutations before you can develop a cancer. It's a pretty cool trick. People actually apply this trick to mice and it works. If you can add extra copies of tumor suppressor genes, it reduces your incidence of cancer dramatically. Naked mole rats have another trick. They have a type of extracellular matrix protein that is kind of creates cages around cells. And so cells can't divide uncontrollably because they're effectively locked in cages. And so when they try to, they just die. So naked mole rats also figured out a way of not dying of cancer, which is cool because their close relatives, mice and rats, actually do die of cancer quite a bit. And that both of those are adaptations that humans don't have. Humans have a lot of other, we are in some ways the pinnacle of resistance to aging, but we're doing it in our particular ways, and we can find other ways, and we can mix and match those and combine them. That's the just learning from nature part. But we can also do de novo engineering we can actually, if we understand aging comprehensively enough, if we look at the compositional difference between an old and a young person, you can just literally identify what is changing. And then you can design new homeostatic methods, whether they be enzymes to break down damage accumulation or just improvements to the metabolic processes such that certain types of damage aren't produced. You could imagine getting your annual software update with improvements to your metabolism that make your ability to maintain homeostasis more comprehensive. And complete comprehensive homeostasis would mean not aging anymore. There's many aspects to this, unfortunately. Like I said, aging is complex. There's thousands of things that are sort of drifting away from homeostasis. So it's a pretty non-trivial task. We don't actually even have a full characterization of everything that changes with aging. We might actually, I think there's probably a lot more that we don't know than we do know. And so this is actually a really big project, and we're talking about spending napkin math, $1 trillion a year for 25 years to even sort of get this project off the ground to the point where we could be significantly extending human lifespan. But it doesn't break any laws of physics. And the technology required to do this is actually being driven by other industries. The AI industry and the synthetic biology industry are building the tools necessary for us to modify our biology, but they're doing it for other reasons, for biomanufacturing and for maximizing click-through rates and generating videos and art and text. So those same tools we will be able to apply to biology eventually. We're in the very early stages of that. Our tools are still too primitive to tackle aging. Aging is is way more difficult than predicting the next token in the way that large language models do. It's a non-linear process. It's a lot of things happening in parallel. But I think in principle, yeah, we'll eventually be able to model aging such that we can design modifications that we expect to be able to extend lifespan. Again, the other problem, though, is how do you actually make the modifications? And that's a really big problem. That's probably the biggest challenge for the bioengineers is how do you genetically modify living humans?
Nanobots. Obviously, nanobots. Are nanobots in the future?
Well, we have nanobots. They're called cells. And so the way to engineer solutions to this is to engineer cells. There's a lot of different strategies. People right now use viruses mainly and lipid nanoparticles to do genetic modification, but they have a lot of limitations. There's major problems called the biodistribution problem. There's toxicity issues. There's immune reaction issues. All of these problems are actually sort of Apollo level difficulty. This is like to solve one of them is like to go to the moon. And so we're not currently investing the resources necessary to solve this problem. We're just making sort of small incremental advances that allow us to treat certain types of rare diseases. But again, like with pharma, the types of gene delivery that we have are just not suited to tackling aging. And so we need much more powerful gene delivery tooling. That's moving forward, but not moving forward fast enough. Most people are focused on near-term applications of the existing gene delivery tools that we already have and small incremental improvements to those tools. What we actually need is radically more ambitious approaches to gene delivery that are completely different than viruses and lipid nanoparticles. And that's probably a 2-hour-long conversation that I maybe won't get into now, but suffice to say, there are out-of-the-box ideas for solving this problem, but they aren't getting the funding that they need currently.
Okay, so let's touch upon that for a brief second. You mentioned Apollo as one of the flagship projects of humanity to achieve something that was thought to be impossible, similar to solving aging. Mm-hmm. How important do you feel is government and policy in achieving the vision of living forever?
I'm a bit agnostic about where the money could or should come from. A lot of people are strongly pro or anti-government. I think we should pursue an all of the above strategy. I think that if you could convince the NIH to divert a larger portion of its budget to these issues, that would be really powerful. Venture capital tends to want things to be on a 10-year timescale for returns. And unfortunately, a lot of the hard technology development projects we need to do are probably outside of what they consider investable. You can also go after high net worth individuals. There's something like, is it 6,000 billionaires now?
I thought it was 3,000, but I might be wrong.
Yeah, I don't know. And collectively, they have enough money to fund this. Interestingly, out of those thousands of billionaires, there's actually only one who spends a significant portion of his money on longevity technology development. And he's unfortunately a bit conservative and focuses more on the drug approach, which we already know won't work. It's called the billionaire paradox in the media. If you read popular news media, you might think that billionaires are putting a lot of money towards this, but the reality is that they're actually not. They're spending less than 0.01% of their wealth on anything that is related to this. And actually, even of that money, most of it is spent on stuff that we already actually know won't work. So it's a bit strange that these people aren't spending money on developing this technology. But the truth is that billionaires are not any different than regular people. They have the same reasons for the same coping mechanisms that make them sort of think that maybe aging is okay, or maybe it's a good thing, or maybe they just don't want to think about it. So it's not a priority for them any more than it is a priority for any random human that you would talk to in the street.
Okay, so I have the last question. What is LBF? What are you doing at the moment? and I know you're fundraising. How can people help achieve your mission?
Yeah, so the LBF is a program for if you want to get involved working in this industry, solving these technology problems, we can help you make that transition. So we have training, networking. We look for scientists, engineers, investors, entrepreneurs, to some degree also community builders and advocates. And we give you the tools that you need and the information that you need to have an impact in this industry. And the reason why we're building what we call the technical roadmap to solving aging is that we want our members to focus on the critical path technologies that are actually needed to solve aging entirely. So a lot of organizations out there, if you're interested in public health, trying to get people to exercise more, to eat better, that's fine. That's not what our organization is focused on. Our organization is focused on if you did everything right, lifestyle-wise, preventative care-wise, you're still getting old. And you're actually not even buying that much time. The difference between somebody who does the right things and the wrong things is maybe 10 years. Depends on the person, depends on what their genetics are. But you're still aging. And that's what the niche that we occupy is the people that aren't okay with that would like to change that think that longer life is better and there's no upper limit to how much more we should be aiming for.
And you need money now, right?
Yes, we take sponsors for our program. Right now, the LBF is entirely volunteer-led, and that limits what we can do. We would like to build a course so we have the LBF program, which you can apply online to go through. It's a cohort-based program. And our members join, start, or support projects in this area. And so it's a great way to get involved if you want to make this your career. But we also want to build a course that is unlimited access because we can only handle so many people one-on-one or even in groups. And so we want to build a course. That's something we're raising money for. We want to build out the roadmap in much more detail. And then yeah, so the roadmap we will be making publicly available. I think by the time that Xenophon releases this, it will be on our website. And so, yeah, if you want to support the work that we do, you can donate to us on the website. You can set up a recurring small donation. Every little bit helps. Or just do it yourself. I mean, our goal is for you to just not do nothing. So if you agree with us that you don't want to have to die against your will, you don't if you ask people in a room, would you like to die against your own will? Generally, nobody puts up their hand, but the truth is that we're actually in that situation already, and people just aren't thinking about it that way. And so the thing that I really care about is that if you agree that you don't want to die against your own will, well, maybe you should actually get involved and try to help solve this problem, because that's the situation that you're in. It might not seem like it today. You might feel okay today. You might be having fun and have some good plans for your next weekend. Everything's great. Life is great. But at some point, aging is going to hit you, and you're going to wish that maybe you had gotten involved earlier. I think a lot of people get old. I know my parents are getting older now, and it's not an enjoyable experience to watch them decline. It's not an enjoyable experience for them either. They would love if there was something that could make them youthful again. Ask any old person if they'd like to be young again. Go ahead, just go do it. You're going to be old too someday. But that's not inevitable. We could do something about this if, as a society, we decided to prioritize it. Currently, we don't. So my ask of you is actually just learn about this and do something. Support us if you'd like to. I think we're doing important work. Support somebody else if you think they're doing a better job, but don't do nothing.
So there's no magic pill. There's no nanobots.
It is a lot of hard work. It doesn't break the law of physics, but there's no silver bullet. There's no shortcut. This is just a very hard research and technology development problem.
And the Longevity Biotech Fellowship is the best way to solve the world's greatest misery.
It's a really good way to get involved and to learn about what are the critical path problems. Yeah. So if you if you want to contribute and you don't know how, that's our job, is to help you figure that out.
Fantastic. Thank you for your time, Mark.